All right, guys, can I get a sound check?
Check.
Yeah, we can hear you.
Great, thank you. Arthur, I like your whatever that is, emoji or your Zoom picture.
Ah, thanks.
That's the singing same as it ever was.
Yeah.
One of my formative experiences. All right. Okay, guys, let's see. How are we doing? We're in the middle. Got good news and bad news. The good news is I moved to another office, so you won't hear snoring. The bad news is my little dog is back and she barks. So excuse me again. Sorry, guys. All right. We're doing, yeah, almost done. There we go. Okay, guys, let's start with a review of what we covered. And this is going to be probably a little bit like, I mean, a long review because I don't know if I made any sense last time, and it's kind of hard stuff to describe. So I'm going to just try to give you guys like everything you need to kind of know in a nutshell, although it's still going to be a while. Okay, so what do we talk about? So we said that, so, you know, we're going to be talking about this material called semiconductors, and that they're kind of in between conductors and insulators. And that in semiconductors, free carriers are responsible for conduction. Okay, and we gave these guys a name. We called the free carriers, like this thing called intrinsic free carrier concentration. Yeah, we call that Ni. And what does intrinsic mean? Intrinsic means that the material is material. So let's, for the sake of discussion, just agree that we're only going to be talking about silicon in the class. I'm just going to say, so intrinsic material means it's only silicon. So the whole crystal is only made out of crystal atoms, nothing else. So in that case, you have basically the conduction is from these free carriers, and their concentration is called Ni. And, you know, we had this really big fruit salad of an equation describing what Ni was. You know, the main thing is that Ni is strong function of temperature. Okay, so a couple of things to remember. So one of them is, a good number to remember is Ni is 1.08 times 10 to the 10th at room temperature. It's a good number to remember. You can always look it up, but that's one of the things I remember. The other thing to remember is that room temperature in this class actually has a definition, which is it's 300 degrees Kelvin or 30 degrees Celsius. Okay, so whenever you see room temperature in a test or homework problem, etc., this will come up over and over again because there's a lot of stuff that's temperature dependent. Okay, just assume that this 300 degrees Kelvin, and everything is, the equations are in Kelvin. So I'm just going to erase this 30C. Just remember to put in all the equations you want to throw in Kelvin. Don't get confused by putting in Celsius. Okay, so, and the things that are responsible for conduction, these free carriers in a semiconductor, and again in silicon, are electrons. And these have a charge of minus 1.6 times 10 to the minus 19 coulombs, and holes, which are plus 1.6 times 10 to the minus 19 coulombs. So this is a charge per electron or hole. And a hole isn't another particle, it's just a lack of an electron, but it acts as a carrier because it's also moving around in your semiconductor. So it's a mobile carrier, but it effectively, from a circuit standpoint, from a current standpoint, it looks like as if you have a positively charged particle moving through your semiconductor. But it's not like it's not like, I'm not claiming there's a new particle out there. It's just a lack of an electron in a crystalline lattice. Okay. So then the next thing we want to remember, or I want to ask you guys to remember from the last lecture, is that we can affect this conduction through changing the numbers. We can affect conduction by changing concentration of free carriers, and we can do this through a process called doping. Okay, so doping means that we are adding another type of atom to silicon. Okay, so initially, when looking at this intrinsic situation, it's all silicon. Every single atom is silicon, nothing but silicon. Here, we can add other kinds of atom to the silicon lattice and sort of create change the concentration of free carriers. Okay, so the first thing I want to say, which I didn't say last time, is, it's for a second there, you got to kind of think a little bit about the numbers, okay? Because they all look big. There's no like frame of reference really. I already failed in my own instructions to you. I didn't put the unit there. This is per centimeter cubed. Okay, so that's the number of free carriers. Now, if you look at silicon itself, so if you just look at silicon like atomic density, so in the same centimeter cubed, the atomic density of silicon is 5 times 10 to the 22 per centimeter cubed. Okay, so basically you can squeeze in, if you had a piece of crystalline silicon, you can squeeze in 5 times 10 to the 22 atoms in a centimeter cubed. So look at the disparity between this number, 10 to the 22, and then the 10 to the 10th in the number of free carriers. It's about 1 times 10 to the 12th. So 1 trillion. Okay. So imagine if, I mean, we have 7 billion people on the planet. If we had one person walking around the planet and it was a different than all the rest of the people, let's say that was a free carrier, he would be 1 in 7 billion. This is much, these free carriers are much rarer. They're 1 in a trillion. Okay, so there's not a whole lot of these free carriers in compared to the number of atoms in the same sort of unit of volume of silicon. Comparatively, there's very few of them. For every trillion silicon atoms, there's 1 of these free carriers floating around. Okay, so basically what we can do is we can still put in a lot of other material in the silicon atom. So for example, let's say we said there are 2 types of material we could dope the silicon with. Let's talk about the first one type, which would be, so remember that silicon is a group 4 element in the periodic table. And that meant that it had 4 valence electrons. Okay, so we could do doping with a group 5 from the atomic table, and that would be, let's say, 2 of them that are commonly used to dope silicon are phosphorus and arsenic. Okay, and these have 5 valence electrons. So they have an extra valence electron. Okay, so every time you throw one of these in the middle of a bunch of silicon atoms, you're going to add 1 extra carrier. Okay, so what you could do is you could, because you have 5 times 10 to the 22, let's say, you put in, worked out a number here. Let's say I do, I add in 5 times 10 to the 13th. So let's say phosphorus atoms per centimeter cubed. Okay. And then, by the way, these are also called donors, group 5. And the reason is I don't know why didn't people name these things, but it's presumably it's donating an electron to the silicon. Okay. So anyway, this is just I'm just throwing a number in there. Let's say you're a silicon engineer. We're not going to go into how you would do this thing, but you can dope the silicon with 5 times 10 to the 13th phosphorus atoms per centimeter cubed. Now notice there's still a lot less phosphorus atoms than there are silicon atoms, right? There is what is that? It's a factor of 9 difference, right? The power of 9 difference between those two going from. So for every billion silicon atoms, I've added 1 phosphorus atom. So it's not like I'm not like saturating the silicon with phosphorus. For every billion silicon atoms, I'm adding a phosphorus. But because we only have 1 carrier per trillion silicon atoms, basically the number, remember each one of these is contributing, because it's a donor, we said it's phosphorus, it's contributing 1 electron per centimeter cubed to the silicon. So basically what you can do is quickly the number of carriers, which are now, remember this is n sub I, which means intrinsic number of electrons. The number of electrons after doping quickly becomes 5 times 10 to the 13th, electrons per centimeter cubed in this example. Okay, so once you start doping a material, the number of, let's say you dope it with donors, in this case, the number of electrons becomes the number of donors approximately. Okay, just because it'll quickly overwhelm the intrinsic number of electrons you had, and you just have to count the number of donors, and that's how many electrons you have. It just doesn't matter how many you had to begin with. There weren't that many. So in the same way, you can dope the silicon with a group 3 element. Okay, and this is the popular one is boron. And by the way, that's called an acceptor. Again, I guess it means it's accepting a electron or absorbing an electron. So anyway, so once you see N sub D here, sometimes this is a density of donors. N sub A will be the density of acceptors, all per centimeter cubed. Okay, so let's say put in boron. I dope this thing with boron, and I put in, so I started with a just regular piece of silicon. I put in 5 times 10 to the 13th boron atoms per centimeter cubed. Okay, let's say. So this was example 1. This is example 2. Okay, so then quickly the number of holes gets overwhelmed and becomes the number of the acceptors that I put in. Again, because the number of holes to begin with was fairly small. It was 1 times 10 to the 10th. I'm sticking in 5 times 10 to the 13th. So I end up make it the number, approximately the number of acceptors. Okay. Everybody with me so far?
Yeah.
Okay.
Sort of.
Yeah. So it just sort of keep that. Okay. What are the main things here? The main thing is in a semiconductor, you can make it be mostly electron carriers or mostly hole carriers, depending on what you as an engineer do to it. So you start with a slab of silicon, and you'll see later why we would want to do this in a couple of slides, but you can make it primarily full of electrons or primarily full of holes, depending on which one of these additional atoms you add to the silicon. We're not going to get into how you would add these in the silicon, but like you can do it. Okay, so that's the most important thing to remember here. Okay, so next thing to remember, again, still from last slide, is that this one you just have to take it as like a rule for this class. We're not going to derive it. That's just how it is. The number of holes and electrons multiplied by the number of electrons is always equal to the intrinsic carrier concentration squared. Okay. Always, 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 always. Okay. So this is a rule, just to remember it. Okay. Why? Just think of it as law, physical law. Okay, which it is. But actually, I don't know if it's physical law, but it's semiconductor. That's how semiconductors work. Okay, so let's look at 2 cases now. Given this, and given this fact that you can quickly become N can either become N sub D when you have a lot of donors in there, or P can become N sub A if you have a lot of acceptors there. Let's look at what that means. So let's take 2 cases again. So for example, if we look at example 1 again, we put in, a bunch of donors, a bunch of phosphorus atoms, 5 times 10 to the 13th phosphorus atoms per centimeter cubed. We put that into silicon, into this chunk of silicon. So that made, like we said here, it made the electron concentration be the same as this. Okay, because there's so much more than intrinsic electron concentration. So now, given this equation, we can calculate the density of holes, because n times p is ni squared, and n is n sub d from here. So p is equal to ni squared over n sub d in this case. Okay, so that's what it is. Now let's throw in some numbers at room temperature. Remember, n sub I at room temperature was 1.08 times 10 to the 10th per centimeter cubed. So this one is 1.08 times 10 to the 10th. Fail, okay. Per centimeter cubed squared over 5 times, sorry, it said 5 to the 13th. It's 5 to the 13th, not to the 3. Times 10 to the 13th per centimeter cubed. And that gives you, I think that gives you 2 times 10 to the 6th holes per centimeter cubed. Okay, so that's the P concentration in this case. In this example, the N concentration was the same as the number of donors. So that was 5 times 10 to the 13th electrons per centimeter cubed. Okay. Any questions about how I got there?
So the N and P, they're separate, right? So yeah, okay. So you multiply
So
them.
basically you just have this 2 flavors of carriers in your semiconductor crystal all the time. But their numbers could be, different depending on how you dope the material.
So it's like if you add in a phosphorus into the silicon, then it's like, is it like there's free electrons in the phosphorus as well, and that kind of comes out at a different rate?
Well, so remember the phosphorus. So the phosphorus atom itself, or the silicon atom itself, and I'm talking about like the nucleus and most of the electrons, or just sitting there, they're not moving at all. Okay, they're just sitting there, not doing anything. Now, when you add phosphorus to the silicon, what happens is one of the electrons in the valence band of phosphorus, so for each phosphorus atom that's sitting there solid, one electron doesn't have anything to bond to, doesn't have any neighboring silicons to bond to, because all those guys are already taken. They only have 4 valence bands. There are 4 silicon atoms next to you, so you got like one one electron that doesn't know what to do. So it starts floating around in the crystal, in your material. Okay, so the phosphorus atom itself is just sitting there, but like it sort of gives off one electron into this piece of material. And now that one electron can conduct electricity or conduct a current. Does that make sense?
Yeah, it makes sense. But didn't you say there was like those electron holes or something, like the silicon?
Yeah. So that's phosphorus. Okay. So the phosphorus has an extra electron. Okay, that's floating around. Then let's say if you had a boron, which is a group 3, it has one less valence electron. Again, it's a boron atom sitting in a bunch of silicon atoms. Everybody's sitting put. This one boron atom is missing an electron, which means that it looks like and that missing electron hole, that hole, which is a lack of an electron, can also sort of float around in your semiconductor. So it looks like that boron atom, which is still sitting still in the lattice, gave off this positively charged particle that then can now conduct electricity. So donors, phosphorus, arsenic, donate an electron. Each atom of them donates an electron, and then you can think of boron or group 3 or acceptors donating a hole or accepting an electron, whichever way you want to look at it. And both holes and electrons conduct electricity. That's what you need to conduct electricity in a semiconductor.
Okay, yeah, that makes sense. So basically it depends on the element you're using.
It depends on the doping. Yeah, what you added to your silicon. And you can affect the concentration, how many electrons, like basically that affects how well you're conducting. If you have a lot of electrons and holes, you conduct pretty well. If you don't have so much, again, not so much. Look at we said if you don't dope silicon, if you don't dope it, for every trillion silicon atoms, there is 1 electron for every trillion silicon atoms. You're not going to get a lot of conduction with 1 electron out of every trillion things around you. Okay, so that's not such a great conductor, but you can make it a little bit better conductor by doping it with these additional atoms. If that makes sense. Now these, again, so anyway, is that a little confusing?
Yeah, that makes sense. Yeah. Thank you, Professor.
It's like, again, this is like, don't feel bad if you got lots of layers of questions, because like I said, this is a deep science in itself, semiconductor physics. We're only just doing the real basic. Okay, just enough so that when we talk about diodes and transistors, we kind of have like a vague idea what we're talking about, because these things will come into those how we build those devices. Okay, so that's how we come up with these things. Okay, so now back to our example 1. Now, so like I mentioned, we have just with these numbers we threw in there. Okay, we ended up with 5 times 10 to the 13th electrons per centimeter cubed. So that's 50 trillion electrons per centimeter cubed. 50 trillion. Okay. And then we have 2 times 10 to the 6th, or 2 million holes per centimeter cubed. So what happened? Because of this equation, because of this equation, okay, if you start putting in a bunch of electrons, your actually number of holes actually shrinks. So now we've got this huge disparity between number of holes. Again, it seems like a 2 times 10 to the 6 seems like a big number until you compare it to 5 times 10 to the 13th. Okay, so you have much more electrons than holes when you dope the material with donors. Okay, because of that, you call this majority carrier, because the majority of the carriers are electrons, and you call this minority carrier. Because you have much fewer holes. Okay, but if you look at example 2, okay, everything flips because we put in a bunch of boron atoms. So we put in the number of acceptors, borons per centimeter cubed. So in that case, the number of holes became this n sub a, which is 5 times 10 to the 13th. holes per centimeter cubed. And it made the electrons, Ni squared over N sub A, it made their number small. So it made them 2 times 10 to the 6th electrons per centimeter cubed. Okay, so in this case, when you put in acceptors, you end up with a lot less electrons than you do holes, like a lot less. So in this case, holes are called majority carriers. And electrons are called minority carriers, because there's a lot less of them than the holes. So the majority and minority changes whether it's an electron or hole, depending on how you dope the semiconductor. Okay, so if you have, okay, so let me get to the verbiage here. So let's say if you have two chunks of silicon. So silicon, case A, case B. Let's say you put in a bunch of donors here. Okay, the majority carriers are electrons. Minority carriers are holes. Okay. And this is also called N-type silicon. There's just a bunch of different names. N-type silicon, because it has a bunch of donors. If we make the silicon, the other chunk of silicon, put a bunch of acceptors there, the majority carriers become holes. And the minority carriers become electrons. And we call this P-type silicon. Okay, guys. So just remember that for a second. Bank it or whatever. We'll come back to it in a little bit. But any questions?
I have a quick question, Professor.
Sure.
So when the majority carriers from the last example, you said the majority are the ends.
Example
more-
one. Which one?
Example one, yeah.
Okay.
So when we have the majority are the free electrons, does that mean it conducts a current, or are you gonna move on to that right now?
Yeah, I'm going to move on to that, but you're right. It'll conduct current. Yeah. So either way, it's going to conduct current. So now, like, okay, so it's either going to conduct as if it's it has negatively charged particles or positively charged particles. But we're actually going to jump right into that. So let me go through that. And
all right.
If you have questions, but it's a good question. Okay, yeah, I don't know if I better not dig myself any deeper in this. Let's just go forward, and then we'll see if it starts making sense. It may not. I don't know. Okay, so whoops. I have these notes. Okay, let me erase this notes because it's going to confuse you guys. Or maybe it was leftover from last time. I don't know. Okay, so now Loe was asking about what's conducting current. Okay, and there are two conduction mechanisms in a piece of semiconductor. By the way, let me just mention one last thing about semiconductors, about the electrons and holes, etc. So if you think of a conductor, okay, so insulators, there's no free electrons, there's no free holes, nothing is conducting anything. You can just put an electric field across it, you'll get an electric field, no current will go anywhere. It's a insulator, right? Everybody like a piece of paper or whatever, you know insulators. A conductor, on the other hand, is like a piece of metal, right? A piece of copper, a wire, whatever. That's just a sea, an ocean of electrons. Completely. Like, it doesn't matter the temperature. I mean, there's some temperature dependence. There's no such thing as doping it with anything. It's just a sea of all electrons. There's also no holes. There's just all electrons. All the time, all the time. That's the only thing that's conducting anything in a pure conductor, in a piece of copper, in a wire, etc. In a piece of semiconductor, because of the way these atoms work and dopants, etc., you have this thing called a hole, which conceptually make things a little confusing, which is a lack of an electron. So now you have two things that are conducting current, either the free electrons or the holes, okay? And then they respond, the only thing is one of them is positively charged, the other one's negatively charged, so they respond to an electric field differently. Okay, so let's first look at the first sort of charge transportation or conduction. So this would be the same as sort of conduction mechanism in semiconductors. The first one is called drift. Okay, and that the important thing about drift is only happens under the influence of an electric field. Okay, so if this was looking at a piece of semiconductor here, okay, that's our piece of semiconductor. We put a positive voltage on one node with this external battery. So we put a positive voltage here and negative voltage here. That creates an electric field from this positive side to that negative side. Okay, and so just remember that electric field is minus dV dx. Okay, so if you put a potential across something, a voltage across this thing, you get an electric field across it, this equation, okay? And then that electric field actually, because you have charged particles, once you have charged particles, they interact with an electric field. Okay, so basically, if you had a positively charged particle, it would start, if you had a positively charged particle, it would move in the direction of the electric field. So it would go in this direction, like these arrows show. Okay, now why is it showing that things are bouncing around here? Because, like we mentioned, you're moving in the middle of a lattice of a lot of atoms, and as you're moving, you only move a certain distance before you hit an atom or you get affected by an atom. So you tend to like bounce around because you actually are colliding with the atoms that are just sitting there. But in general, you have this movement from the, in the direction of the electric field, but you tend to bounce around a little bit. Okay, so basically you have this factor where the velocity of electrons or holes. So let's say, so again, sorry, let me start with the holes first. So remember, holes are positively charged. So that means the holes are the ones that move in the same direction as the electric field. So if you look at the velocity of these holes, so V sub h is in the direction of the electric field, so it's positive. And then because you have this scattering, you have these things that keep you from going straight in this one direction, you have a proportionality constant. So they took all these, averaged all these collisions and all this stuff up and came up with this proportionality constant between velocity and electric field called mobility. So this is called mobility. mu sub p is the mobility of holes in silicon. Okay. And then if you're an electron, remember electron is negatively charged, obviously. So electron is negatively charged. So it's actually an electric field is going to make it move in the opposite direction. So if you had, if these arrows were representing an electron, it would actually, all the arrows would sort of point in this direction because they're going to go, because it's negatively charged. If the electric field is pointed in that direction, the electrons are going to move in that direction. So that's, it has this negative sign for the velocity of electrons. And they also have this proportionality constant. And this mu sub n is mobility of electrons in silicon. Okay, so that's called drift. You put an electric field across a piece of semiconductor that has free carriers. The electrons are going to move in the direction opposite to the electric field, and the holes are going to move in the direction with the electric field. Okay, and they'll have some velocity that's dependent on this proportionality constant. Okay, and I'm not going to work through this. It's given in the book. This is one of the stuff that I'm just going to like leave for you guys to take a look at if you're curious. But basically, these movement leads to a current, right? You're moving electrons and holes, you're moving carriers, you end up with a current. We end up, it's a geometrical calculation. So given the velocity, the width and height of this chunk of stuff, the fact that you have a certain density of free electrons and the charge of an electron, you end up with a certain current. Okay. Same with the holes. So when you look at the current density, so I is, current, obviously. J is current density, which means current per unit area, per unit cross-sectional area. So that means if you have, how do I draw this? I do such a bad job at drawings. So let's say I had my piece of silicon. I had my electric field going from one side to the other. This cross-sectional area would be sort of this area here. That would be your cross-sectional area A. So the wider this thing is, the lower the current density for the same current. Okay, so people think about in terms of current density because then you can leave out how thick this piece of silicon is, etc. But the things to remember, let me see if we have a quick equation for current. No, we don't. So this current density is the same as current essentially, just for this, except it's per unit cross-sectional area. Okay, so basically you have two components because of this drift type current or conduction. Okay, you have the electrons and you have the holes. Okay, now remember, because this is dependent on the electric field, the electrons are moving. So, in a piece of semiconductor, we have both electrons and holes. There's not the same amount. Like we said, sometimes you have more than the other ones, but you have both all the time. You have both electrons and holes. Okay, so when you have this drift current, it's made out of both of those components moving because of the electric field. The electrons are moving in the opposite direction as the electric field. The holes are moving in the same direction as the electric field. But because the current, this is going to confuse you guys, because the current of the electrons is made out of negatively charged particles, or negatively charges, then it's like it's moving in a negative direction because of the electric field, but you multiply it by the charge per unit electron, so it's negative times negative, it makes it positive. So basically those two currents just add the hole and the electron currents add together and are a function of electric field. Okay, so that's your drift current. That's the first conduction mechanism in a semiconductor. It's okay. The important things to remember about it are that it's caused by the electric field, the direction is set by the electric field, and that the electron and hole components of that current add together. Okay, so those are the main things besides the equation and stuff. Any questions so far? So that's your one.
I do.
Yeah, go ahead, Arthur.
What is after current for what J stands for?
What is?
G,
Sorry.
you know what the J equals to? I can't read it after current. It's like on the right.
Oh, here.
Yeah, here.
Oh, sorry. Okay. It's current density.
Oh.
And it's current per unit cross-sectional area. Okay, so imagine this is one way to look at it. Imagine if there was a water current. How far are we doing on time? Yeah, we're doing okay. So imagine if there was is the class till 6:45 or 6:30? I keep forgetting.
6:45.
Okay, great, thanks. So imagine if you had a hose that was yay big and another hole that was much bigger. Okay. So the cross-sectional area of this guy is smaller than the cross-sectional than this guy. Okay. Now let's say you had the same water flow, okay, through both of them, through both the small one and the big one. So the density of the current going through this small one is going to be higher because all that water current's moving through a smaller cross-section than when you put the same current through a bigger cross-section. So the bigger thing, the bigger, wider hose has a smaller current density, although it's the same current. Okay, so now the question is like, hey, why do I need to worry about both current and current density? It's just because people want to not think about, these are derivations, so they don't want to think about cross-sectional area. They just want to take that out of the picture. So they start talking about current density.
Okay, that makes sense. Thank you.
But don't stress too much about it. Again, we're really what we're after. The density thing will come here and there, but the real thing to think about is we're thinking about a current, conduction, right? And that the conduction, there's two components of conduction. The first one is drift, which is dependent on electric field. Both electrons and holes are involved. They're both going to add together because the electrons have a negative charge and they're going in the opposite direction. So they both add together. It's dependent on the electric field. So those are the stuff to keep in your head about that. Okay. Anything else? Any other questions, I should say? Okay. So now this velocity saturation is getting too deep. Don't even bother with this one. Don't think about it. So just keep that in your head. So the second thing is the second mechanism. So we talked about drift. Now there's another conduction mechanism called diffusion. So what's diffusion? It's not dependent on electric field. So drift is dependent on electric field. So remember that diffusion is not at all dependent on electric field. So how do you think about diffusion? It's basically like, think of it if you had, anyway, I don't know if you guys use ink or not, but if you had, let's say if you had a glass of water and you put a drop of ink in that glass of water, that ink starts spreading through the water, right? You're all familiar with that. Eventually, it turns out that ink gets uniformly distributed through the water. It goes down, it doesn't have anything to do with charge or semiconductors or electron, is just a mechanism because of the Brownian motion of particles, which is just like a fundamental physical thing. When you have it turns out when you have a low density of something in one area and is free to move to other areas, that thing tends to distribute evenly in that area. So for example, another example is if you're cutting an onion in a kitchen, the smell, which are like sort of these atoms of whatever is causing this smell of the onion, it sort of starts close to the onion and gradually spreads through the whole kitchen. So the whole kitchen becomes uniformly this distribution of this stuff. It just, whatever has some density, like a gas, you put in a gas and a volume, eventually the gas will uniformly distribute itself everywhere. And what's going on there, what's going on is stuff is moving from a location of high density to a location of low density. Okay, if you think about it, any questions about that? It's just like a fundamental thing, and we just don't even think about it in terms of semiconductors. It's just what happens in life. It's just called diffusion. Okay, and it doesn't even have to do with, it doesn't even have to be a charged particle. Like I said, it could be ink and a glass of water. It could be, atoms in atoms in a volume of something and then spreading and so on. So that's called diffusion. So what does that mean if we think of it in terms of a semiconductor? It means that if we put a bunch of carriers, let's say a bunch of electrons, on one end of a chunk of semiconductor, okay, so we'd have a bunch of carriers here because that's where we're injecting them in. Here on this end, there isn't a lot of carriers, right? So what happens is these guys are going to start going from a place where we have a lot of carriers to a place where we don't have many. So you just get these carriers moving in a direction where there aren't many of them. So if you can think of it as, if we're dumping a bunch of electrons here, the electrons are going to start going to where there aren't that many electrons in the semiconductor. Okay. Same at holes. If you put holes here, they're going to start chugging along to where there aren't a lot of holes. They just diffuse out. Stuff that's free to move goes from high concentration areas to low concentration areas. Okay. Any questions about that?
I had a quick question.
Sure.
So I'm not sure. I think I'm kind of studied this thing before. Maybe there's an example. I'm not sure if this is related to this topic or not. Is that something related to lighting?
To what, sir?
Lighting, like the clouds, the lightning.
Lightning, my knowledge of lightning is close to zero, but the way I understand lightning, it's actually that you sort of build up a high enough electric field, and at some point that electric field is so high that the air, once you get electric field across a insulator, like a piece of paper or whatever, once the electric field gets too high, that insulator breaks down and actually conducts. But I mean, it's a very high electric field. And so that's my understanding of what happens in electric field. You basically get, the clouds have such a huge amount of charge built up compared to the earth that so you got a lot of charge, not much charge. You start building up an electric field, and at some point the air breaks down and all that charge gets dumped in. So it's not quite the same. It's actually like a breakdown of a insulator, which is air in the case of lightning. which is,
so
yeah.
it's a different topic.
I think it's a different topic. I hate to say it's, you know, like in the end, all these things may be the same. You know, I think it's somewhat different. This is like easier to think about it in terms of ink in a glass of water or something like that, because it's not an abrupt thing. That's sort of a difference between lightning and this. Lightning is the kind of thing where it gets built up, built up, built up, and all of a sudden you discharge. This thing starts going slow and steady the whole time. So it's maybe another way to look at it. So it's just from the get-go, it starts going, and it's just sort of like this slowly happening event.
Thank you.
Sure. But warn you, I don't know anything, like I barely know anything about lightning. Okay, so let's now take, any other questions? No? Okay, so let's take, this is gonna seem like a crazy example, but now let's say somehow, we're not gonna talk about the how, you'll see in a few slides why. Let's say you inject these carriers in the middle somewhere of your semiconductor, okay? Now what happens? Well, you got a bunch of carriers here in the middle. You don't have so many here or here, so the carriers will start going into both directions. Okay, so just from high concentration to low concentration, high concentration to low concentration, that's it. Okay, these carriers are just gonna go. Okay. So, and the other thing about this is that the rate at which these carriers move from high concentration to low concentration has to do with the concentrations. Okay, so if you have a huge concentration of carriers here and very small concentration, you get a huge amount of movement of carriers. If you got sort of a small amount of carriers here and sort of small, so you don't get so much, right? So if you look at the current caused by this diffusion mechanism, here's the equation for it. Again, I'm not going to drive it. It's a function of this, you know, change in the carrier concentration across distance, okay? And, you know, the charge of whatever's doing the conduction, whether it's an electron or hole. And, you know, there's this thing called a diffusion constant. That has to do with how well this diffusion happens in silicon. So it's a function of it being in silicon. And it's a diffusion constant for holes, and there's a diffusion constant for electrons. So there's this diffusion constant term for electrons and holes. Okay, so this is current flow. Now, in this case, again, you have diffusion current for both electrons and holes in a piece of semiconductor, but both always present. Remember that in the case of a drift current, those two currents added together because we had two negatives. The electrons were moving in the opposite direction of the electric field, and they had a negative charge. So those two made that current effectively a positive current. And so you just added it to the positive current of holes, okay? Now, in the case of diffusion, that doesn't happen because the electrons and holes are both moving in the same direction. They're just moving from a place of high concentration to a place of low concentration. There's no electric field that they're responding to, okay? But the electron still has a negative charge and the hole has a positive charge. So, but there's nothing to sort of cancel out the negative electric charge of the electron. So you end up having sort of a negative direction. So they basically are fighting each other, the electrons and the holes. Okay, so it's electron minus the hole current. So basically you have, they don't add, they subtract from each other. Okay, it's kind of the thing to remember. Okay, so this is an example of, I'm not going to go through this, but they're basically depending, it's a physical phenomenon because you're going from high concentration to low concentration. So depending on the profile of the charge carriers, you could get either a linear movement or you can get an exponential movement. I'm just going to leave this alone for now. We'll come back to it in a bit. Okay. So any questions? So I'm not, let me rewind and again say that you have the main things to remember is you have two conduction mechanisms in a semiconductor. One of them is electric field dependent. That's called drift. Okay, in which case the electron and hole currents add together, they're working together. And then the second mechanism is called diffusion. It's not dependent on electric field, and the electrons and hole diffusion currents are working sort of against or just subtract from each other. Okay, but they are not dependent on electric field. Any questions? No. Okay, you guys are all sufficiently confused, or yeah. Okay, so this is just kind of a funny fact. Actually, it's not quite a funny fact, but for the case of um, in this class, it doesn't really matter. There's this actually a pretty important relationship that links drift to diffusion because, you know, we got the diffusion constant. Whoops, you guys can't see my cursor. You got the diffusion constant here. Remember, this was a function of the diffusion current, and you have the mobility, which is a drift component here. And it turns out that they have a set ratio somehow. Somehow they have a set ratio. This K is a universal constant called Boltzmann constant. Temperature is temperature, and Q is the charge of an electron. So it's kind of magic. I think that's what the author is saying. It's pretty cool that although you have what looks like two completely independent mechanisms, which is diffusion and drift, somehow the ratio of those two things, ratio of these two constants, is actually a constant. So anyway, but you guys can just ignore that for time being. I just thought I'd add it to help with the confusion. Okay, so there we're done, guys, with slide deck 1. Now we're going to move to slide deck 2 if I can. Can I? What happened? Doesn't want to. Just froze. Sorry, guys. Why am I frozen? Okay, so deep breath. Everybody ready for the next batch of next giant step here? So, like we talked about, you can make a piece of, you can make a piece of semiconductor N, and you can make a piece of semiconductor P. You make this N by putting a bunch of donor atoms, which are again phosphorus, etc. And you can make this a P or acceptor by adding a bunch of, let's say, boron. Okay. So we all saw that in the last set of slides. Now, nothing says that we can't take a piece of silicon and like dope half of it with donors and the other half with acceptors. There's just one piece of silicon. So that means those two, the N type and the P type, the part with the acceptors, the part with the donors, are just stuck to each other. They're kissing up to each other. So basically you end up in this situation where you have this N material stuck to this P material. Okay, there's no glue in between or anything. There's just like a piece of semiconductor on one hand, on just one side here. It's all, you know, phosphorus doped, and on this side, it's all boron doped. And you can make that a real sharp transition. Okay, so you can do that. And it turns out that that creates a so-called PN junction, which in a circuit term gives you a device called a diode. Okay, which is the first device we're going to talk about. And what does this device do? Turns out that the device, if you take your diode and you put a voltage across it. Oops, didn't give myself a lot of room here. Let me. So it turns out if you get a diode, you put a voltage across it. And this diode is nothing but like a piece of semiconductor where one end is N-type and the other end is a P-type. Okay, so if you did this, you're gonna get a strange, funky, but very useful characteristic. So if I plot the voltage versus the current, okay, I can approximate it like something like this. Okay, at some voltage, V sub D, we'll look into how you calculate V sub D or how do you move it and what it does not conduct until you get to V sub D. And once you get past V sub D, it conducts like very, very well, like basically with like zero resistance. Okay. So basically that diode is this PN junction, which is a piece of silicon with N doping on one side and P doping on the other. Okay, so the rest of this lecture, we're going to talk about how from this thing, from this guy, you end up getting this funky curve. Okay, and the next chapter, we'll look at if you have this funky curve, what kind of circuits you can design and, you know, what kind of interesting things you can do and how to analyze it, etc. So first, let's look at how from here we can get to here. Okay, so let's see, what does this look like? This looks like you are overcoming some barrier somehow, right? That like you were applying a voltage or applying an electric field across this, you apply a voltage across this guy, nothing happens, nothing happens, nothing happens till you get past a certain point and then the thing turns on. Okay, so some kind of a mechanism like that, but you have to overcome some kind of a barrier. So let's see, where does that barrier come from? Okay, so now I have to remember the previous slide, previous lecture deck. So we have a N-type. So we stuck a bunch of donors here. And we have a P-type. So we stuck a bunch of acceptors here. So this is our PN junction, right? So what does that mean? Well, okay, if we put a bunch of donors on this N material, we end up with a very, very large number of electrons and with a comparatively smaller number of holes. Okay, everybody okay with that? So donors, remember that that we did the examples. The number of electrons when you put in donors is the same as the number, as a density of donors, and then comparatively, and that makes them the majority carriers. And then comparatively, the other type of, so in this case, it's electrons. So holes, their density goes down and becomes relatively small. Okay, so any questions about this point here? Okay, So when you have acceptors, the reverse happens. You end up with a bunch of holes, like that becomes the majority carrier over here, and comparably a small number of electrons here. So a lot of holes here, not so many electrons, a lot of electrons, not so many holes. Okay, so now for a second, look at just the electron carrier concentration, which is just, I'm just going to highlight it in green. It's not much of a highlight. Okay, so just look at the electron carrier concentration from the N side going to the P side. Okay, here we have a lot of electrons. Here we don't have a lot of electrons. You know, it might be by 6 order of magnitudes ratio. Like it might be like 1,000,000 times more electrons here than here, depending on the concentrations of electrons and holes. So you have a huge amount of carriers here, of electrons here, not so many electrons here. What do you, any guesses as to what's going to happen?
They're gonna move to the other side when we get to VD.
Exactly. So basically all the electrons are going to want to start going from here to here because of diffusion. When we have a lot of something, it's going to want to move to where there's not so many of it. Okay, so they're just going to start going. That's what they want to do. Same with the holes. The holes, you got a lot of them here, not so many of them here. So all the holes are going to want to move in this direction just because of diffusion. Okay, so if you build,
Are they gonna be disputed in E?
Sorry.
What would be the new, like, kind of like a ratio or like a percentage of what will happen when we get to V?
Equilibrium? Like if you just wait there a long time, what happens? So it's something unexpected happens, because if you would think, well, like in the end, what would happen is it would even out, right? If you just look at electrons, so like a glass of ink, sorry, a glass of water with a drop of ink in there, you'd say, okay, well, that ink is going to evenly distribute everywhere. So if I have a high concentration of electrons here, low concentration, you would think if I wait long enough, it's going to be the same concentration everywhere on both sides. Same with the holes. It's not what happens, but that's sort of like would be your first thought. Okay, but that's not what happens. And because something else kicks in. And what is that something else? Well, so and does that, Lloyd, is that?
Yeah, it's clear. I just wanted to see, like, is there a ratio? But you made it clear with the water example with the E.
Yeah, it'll just try to even out. That's what it would like to do. If there was no other mechanism at play and we only had diffusion, the ratio would be 1. It would try to be just completely even. Okay, it'll take it a while to get there, depending on this time constants and stuff, but it'll get completely even. Okay, but there's other mechanisms in its semiconductor. Okay, let's talk about that. Okay, so let's look at what happens with time with this stuff. So first, you're in a situation where you have a lot of electrons here and a lot of holes here. Okay, so now all these electrons are going to start moving over here. Okay, so okay, sounds good. So now these electrons have left the N side and moved into the P side. Okay, now you got to remember one thing, right? Those phosphorus atoms that we said gave up their electron. Okay, stay with me for a second. Remember we said there's phosphorus atoms sitting there going nowhere. They gave their electron up to the silicon lattice that they're sitting in, okay? Now, that phosphorus atom has a certain positive charge in its nucleus. Okay, just go back to atoms. So the nucleus is positive charge. It's the same as the negative charge in all the electrons in the outer shells of this phosphorus atoms. Now that phosphorus atom gave up an electron. So, you know, if you just think about the phosphorus atom itself, it seems like it should be kind of like now ionized, right? It gave up an electron, so it should be positively charged if you just think of the phosphorus atom by itself. This is it's called ionization, okay? But that electron, if you look at that whole piece of semiconductor, that electron is still floating around that piece of semiconductor. So as a whole, that piece of semiconductor is still neutral, okay? But that phosphorus atom there, sort of, you can think of it as being positive charged, but its electron is still kind of around there somewhere, right? So as a whole, that piece of semiconductor is still neutral if that electron did not leave that piece of semiconductor. You guys with me?
Yeah, we're with you.
Okay, great, thanks, because it's sort of confusing.
Trying.
What's that? Arthur, you just sounded
Trying.
side. Okay. Well, just it might take a couple of times to get this thing. So anyway, but here, what happened? Well, that piece of that electron moved to the other side, so we just lost them, right? So that means we became positively charged. So every electron you lose, like because of diffusion, these electrons are moving to the other side. But every time you lose an electron to the other side, you become more and more positively charged, your side. And the same thing is happening to the holes. Those boron atoms, they gave up their holes, is a way to look at it. So those boron atoms, the holes are moving to the other side. So those boron atoms are, this piece of semiconductor is starting to get negatively charged, okay? And basically things start to get positively charged or negatively charged close to this border, okay? That's where it starts. And as time goes on, as more electrons go to this side, this region expands this way into the semiconductor, and this region expands this way into the semiconductor, okay? So what happens is you get a region in the semiconductor. This is a physical region in the semiconductor close. So this is called, by the way, this is called the junction, is where the N touches the P when you built it, okay? So this region around the junction on the N side starts getting positively charged, and the region in the P side start getting negatively charged, okay? And this region ends up being called the depletion region. Why is it depletion? It's deplete because it's depleted of free carriers. Whatever free carriers, like whatever electrons were sitting here, they popped over to the other side. So now there aren't any electrons here. So you only have these positively charged ions, okay? And same here. All the holes having to do with these boron atoms, they went over to the other side. So you only have these ionized boron atoms there that are negatively charged. So there's sort of, this region is depleted of free carriers. So it's called a depletion region. Okay, you with me? So I'm taking you down this storyline here. So,
Yeah.
okay, okay, now we got positive charges in here, negative charges here. what happens when you have positive charge and negative charge? You get an electric field. Okay, so what happens is because you have these positive charges here that are sitting there, like they're just ionized atoms that they're not moving, they're just sitting there, and they're negatively charged ionized atoms on the other side that are also not moving. You'll get an electric field from these positive charges pointing to the negative charges. Okay, so you get an electric field from the positive side to the negative side. Okay, and with time, this electric field starts building up. The more electrons leave this side and go to here, the bigger this electric field becomes. Okay, so the timing goes, these two guys happily get together, boy meets girl, whatever you want to say, okay? And as time goes on, electrons, because of diffusion, move to the other side, holes move to this side, and you start getting these ions, and an electric field starts building up. So electric field is building up, building up, building up. Now, this is where the magic, I don't have to call it magic, whatever, this is a weird, unexpected thing happens. Now look at the direction of this electric field. This electric field is pointing, like you would think of an electric field would, from positive charges to the negative charges, okay? So an electric field that's pointing in this direction is gonna push electrons in that direction, okay? Everybody with me?
I think, yeah, because the electrons always try to go to the positive side.
Yep, they're just going in the negative directions of the electric field. So what is that? What happens there? You got electrons that want to come to this side because of diffusion, but because of that, my battery's dying here. Oh, it's still alive? No. Surprise. Sorry guys, I thought I'd lose my camera, but I guess still going. So sorry for the interruption. So because of diffusion, electrons move from the n side to the p side, but all that diffusion creates an electric field that fights against that wants to push them back. So this creates a resistance to itself, and this is kind of like a negative feedback. It's a self-limiting mechanism, okay? At some point, the electric field gets strong enough that it stops. That's exactly strong enough to stop the diffusion current. So basically what happens is you end up with these positive charges, you build an electric field, and at some point, basically it stops diffusion of electrons to here and holes to here, okay? And you just, even without applying, this confused the hell out of me in undergrad, without applying an external electric field, you get an electric field in this area around your junction. And that's called the built-in, this is too thick, built-in E field, or more usual built-in potential. Okay, so basically if you put a N and P junction, sorry, if you put a N and P material together, you end up getting an electric field between them without having to apply one externally, okay? Any questions? Oops, guys, sorry, I just realized we ran over time. So let's leave it there. Any questions?
Will you have the slide deck on the like on Blackboard?
Yeah, I sorry, I put it in kind of late this afternoon, so it should already be there.
Okay, yeah, thank you.
Okay, guys. Good luck absorbing all this stuff. I'll talk to you guys on Tuesday.
Thank you, Professor.
Professor.
Thank you. Thanks.
Thank you, Professor.
Thanks. Bye.